Good afternoon and welcome to the UMass Extension Greenhouse Lunchtime webinar. My name is Jeffrey Joy and I am your host for the webinar. Our speaker of the webinar is Dr. Rose Rodares, who is an assistant professor and greenhouse extension specialist with the University of Connecticut. In this presentation, Rosa is going to discuss how to identify and manage the symptoms of iron deficiency and toxicity on spring greenhouse crops. If you have any question during the webinar, please type it on the question box, and at the end of the webinar, my colleague Tina Smith will read the questions and Rosa will provide the answers. At this point, I'd like to pass the controls to Rosa to continue with the webinar. Rosa, is all yours now.
Okay. Can you see my slides?
Yes.
All right. And can you hear me okay?
Can hear you okay.
Okay. So thank you, Jeffrey, for having me here. So I'm going to talk about iron deficiency and toxicity. We're going to talk a little bit about identification, but we're going to spend most of our time in management. So my email is there on the screen, so you can write it down if you have further questions after the presentation. I'm always open to help everyone. Doesn't matter the state. And then I would also like to acknowledge that most of the photos that I'll be using today are from Dr. Paul Fisher from the University of Florida. He very gracefully shared his photos with me. So, so the first thing that we need to know when we think about iron deficiency and toxicity is that plants differ on how they uptake iron. So we have this group of plants that are very efficient in uptaking iron and this group of plants that are inefficient uptaking iron. So for example, if we look at the first photo on your left, we have an iron inefficient plant. And these are plants that they need a lot of iron because they don't take it very well. So in order for them to supply enough nutrients that they need to have enough iron in the root zone. Otherwise, they don't grow well. In this group of iron, we usually have what we call the petunia group. So from now on, every time I say petunia group or iron inefficient, you know I'm talking about the same thing. And then the petunia group grows really well between a pH of 5.4 and 6.0. Then we have the middle group of plants called the general group. In this group, it's kind of in the middle. They grow well at a wider range of pH. But their optimal pH would be 5.8 to 6.4, and we're going to talk about this group as well. But we also have the other extreme where we have iron-efficient plants. And these plants take very little iron to supply their needs. But the problem with these plants is as well that if they have a little too much, they also have this tendency to run into iron toxicity. And this is what we tend to call the geranium group. And this group grows best as pH is 6.0 to 6.6. So the first thing we need to know is that plant species differ in their response to media pH. So it's very important when we think about I'm growing this plant, you want to know whether you have a plant that is in the iron inefficient group or the iron efficient group or the general group, because that's going to help you identify the problems or even prevent the problems from occurring. So as you're going to hear throughout the presentation, a lot of what I'm going to talk is about pH, because when we talk about iron, pH plays a major role. So when we look at the pH of the growing media, it affects the nutrient solubility and therefore it affects plant health. So if you look at the bottom of your screen, and you see that what we have on the x-axis there is the pH of the growing media, and then you see all those elements listed where you can see the relative nutrient solubility. This means that, for example, if we just pay attention to the iron is present in the growing media, but as the pH changes, the availability of that iron for the plant changes. So when we look at iron and we look at the lower pHs, we can see that iron becomes more available, right? As the pH goes up, iron becomes less available, right? So we tend to think about iron becomes less available as it turns into forms that look very much like rust. So plants cannot uptake that form, so it's less soluble for the plant to uptake. So we tend to draw that line at pH 6, where we said in general, micronutrients are more available when the pH is under 6, and more available when and less available when the pH is higher. So I draw this graph, which is not a real representation of how iron behaves because it's not a straight line. But what I wanted to point out in this graph is a simple way to remember: the lower the pH, the higher the iron; the higher the pH, the lower the iron. So basically, again, it's not a true representation of how iron behaves with pH, but it's really a true representation of they have this inverse correlation on how the solubility is available for the plant based on the pH. Again, we draw the line at pH 6, and what we need to think about is that if our growing media is under pH 6, the plants that will grow best are those plants in the petunia group that are not as efficient uptaking plant because they need more availability of iron in the low pH. And then we also need to think that under that pH, our geranium group will have a potential problem to result in iron toxicity. And then if we look at the other side of that spectrum, we can also see that plants that grow best will be iron with efficient plants because they don't like to have a lot of iron in the roots. Again, this is the geranium group. And then the potential problem is if we are growing crops in the petunia group, they will be prone to having iron deficiency at that pH. So again, thinking about how those two groups are in a different spectrum and how their needs are different across the pH spectrum. So now when we look specifically at each group, we can see that the iron efficient plants, they like to have high iron in the growing media, high solubility of the iron. If the iron is over 6.4, you will start seeing deficiencies, and we're going to talk about how to identify those deficiencies. And then the other thing is that the optimum pH goes from 5.4 to 6, and other plants that belong to this group are azaleas, bacopa, calibricoa, dianthus, nemesia, pansies, petunias, rhododendrons, snapdragons. So even though we're talking about these plants having being prone to nutrient deficiencies, to nutrient deficiencies when the pH is high, these plants, you can also see toxicities, and we're going to talk about that at the end of the presentation. To identify the symptoms, there's two things we always want to look at. One is we want to understand what's the function of the element, and then we want to know how the element moves in the plant. So when we look at iron specifically, the function of the iron in the plant is to synthesize. It's involved in chlorophyll synthesis. It's involved in nitrate reduction. In other words, it changes the nitrate inside the plant so the plant can uptake it, and it's also involved with other enzymatic functions. So again, thinking about how the function can affect the plant, because it's so involved with both nitrate reduction and chlorophyll synthesis, the typical symptoms of iron deficiency is to have the intraveinal chlorosis. And it's very characteristic of iron, and that's because iron tends to accumulate on the veins. So that's why we don't see the deficiency or the chlorosis on the veins, but we do see it on the rest of the cells of the plant. And then as the symptoms progress, advanced chlorosis will develop, and you can see that plants can be as white as what we call bleaching of the leaves. But you can see that you still get slightly green veins, even though the chlorosis is pretty advanced. The other factor, again, when we look at trying to identify whether what's causing a nutrient deficiency of toxicity is the mobility of the element, we know that iron is an immobile element. And that means that once the plant uptakes the iron doesn't move to other parts of the plant. So the plant, in order to supply iron to other parts, it needs to be uptaken. So when that happens, if there's low iron levels, you will first observe deficiencies in the younger tissue because the iron is uptaken, right? So the older tissue has some iron, and then the younger tissue will not have iron because not more iron is being supplied. So you will first see symptoms in the younger tissue. And the opposite would happen with toxicities, right? You tend to see toxicities first in the older tissue because they tend to accumulate before they get translocated to the newer tissue. So in this photo, you can see we have younger tissue here, calibricoas, burned. You can see this bleaching as well of the deficiencies being observed first in the younger tissue. And then again, I will emphasize this many times. Iron deficiency will occur most likely at high pH. We talk about how Calibricoa belongs to this group of plants. You can see that these plants had the exact same nutrients, but they were just, the pH of the growing media was changed. You can see the lower the pH, the happier the plant will grow. So now we're switching to another group, right? We have these iron efficient plants. Again, these plants are very, very effective in uptaking iron, so they don't need too much. And they are also very effective uptake in manganese. When we have the pH under 6, again, the lower the pH, the higher the elements, we tend to see toxicity. So geraniums are prone to having this toxicity, and therefore the optimum pH will be between 6.0 to 6.6. And again, here is a list of the plants that belong to this group. So if you have these plants, think about, we don't want to have the pH on the low end. Now we're going to switch to iron and manganese toxicity with low pH. So the way we want to identify the symptoms is, first of all, to think of, because we are talking about low pH, and if you remember that graph where I show you all the other elements that were also affected by pH, it's very hard that when we have a toxicity caused by changes in pH, that we will see the symptoms alone. So in this specific photo, when we have low pH, you can see in the right photo that the plant starts to show symptoms. You can see some burning of the leaves. That's caused, again, by the combination of both manganese and iron. Iron toxicity doesn't have very specific symptoms, so it's hard to identify just because of the symptoms. So you have to use your other tools, looking at the growing media, understanding the plant, and tie that together to the symptoms. But the symptoms alone are very hard to use as an identification tool. However, when you put together, every time we think toxicity, and here we have another example of manganese and iron toxicity together, you start to see the margin of the leaves being burned, and then you can see it here in the lower leaves. You can see that the green is not as deep green as a healthy plant, and then as the symptoms advance, the burning is really aggressive. So again, in this case, when we're thinking about iron toxicity caused by low pH, they usually tend to go hand-to-hand with manganese toxicity. And I'll show you some more examples at the end of the presentation. And then just to talk a little bit about the general group, we have plants that grow at optimum pH, more in the middle. They're not as specific as the other two groups. So here are some plants. But I will also show you that if you look at this photo, the plants still have an optimum pH. They can be neutral, but that doesn't mean that they don't have an optimum pH for them to grow. We always say that when you don't know what pH to grow your plant, grow them in the middle, around 6. 7 is already too high. So just a good way to start. So the first take-home message for today is that plants differ in the efficiency in which they uptake iron. The easiest way to remember that is a happy petunia is a sad geranium and vice versa. So make sure that if you're growing both, keep in mind that you need to treat those slightly different or try to be as much in the middle as possible. And then the other thing, the most important probably, is the pH will affect the iron solubility. Again, the easiest way to remember is as one goes up, the other goes down. So you can remember, if my pH is too low, I'm risking toxicity if I'm growing geraniums. If my pH is too high, I'm risking deficiency if I'm growing anything in the petunia crop. So now we're going to talk about management. And always when we think about management, we've got to think about all the tools that we have to prevent management from occurring. We want it to be preventive. I always said, let's start with the water quality. It's very important. The first reason is that the total alkalinity is, if you think about alkalinity, that's kind of thinking about dissolved limestone in the water. That will affect your pH. If you think you have a lot of alkalinity, you're pouring dissolved limestone every time you're irrigating your water. You want to check the iron levels. There's some water sources that have high iron levels, so you might be bringing a toxicity just from water. And then I cannot not say this, just check the EC in general as a good practice. And then if you get a water test, I always tell my growers that I help them make interpretations and develop nutrient management based on their water quality. So feel free to email me if you test your water quality, and I can look at it together and help you make interpretations of what that means. And just very briefly, one of the most important things when we think about alkalinity is that alkalinity is a stronger base than pH. If you look up here, if you were irrigating 1 liter container with 1 liter of water for 15 weeks, and you want to see what the effect of a pH 9 would have on the growing media, or the alkalinity of 200 parts per million, we can see that when we compare these apples to apples, we can see that the pH only had a 0.15 milliequivalents of base that was added to the growing media, whereas the alkalinity added a 60 milliequivalents of base. So alkalinity is a very stronger, it's a stronger base than pH, and that's very important to know, because many growers are trying to work on around the pH, and it's really trying to compensate the alkalinity in the water that's the most important when we think about pH management. So the second thing is that we need to understand the fertilizer label. Ammonium fertilizer is very acidic, and that's true for urea as well. So when you look at your fertilizer label, if you have a lot of ammonium and you have problems with trying to keep the pH up, you need to knock down the amount of ammonium that you're using. If we think about nitrate, the other nitrogen source, nitrate tends to be a weak basic. So again, if you're having issues with trying to keep the pH up, again, keep in mind that we need to look at the label up close. This is a table that I took off from the Griffin website. You can see that the industry has done a lot of work trying to help you understand what's in their fertilizers. And one of the examples here, we have 2177. It's a very strongly acidic. You can see that all the nitrogen is in the form of ammonium and urea. So if you're thinking about pushing the pH down, 2177 works like an acid. It's one that you need to use with caution, and we'll talk more about it. But just so you know how to read the label. And for example, if we look at 13213, you can see that 93% of that nitrogen is in the form of nitrate. So this tends to be a very good fertilizer to maintain the pH, especially if your alkalinity is really low. If your pH is tends to go down, you want to use a fertilizer that's along these lines. So the rules of thumb for selecting fertilizers is, if you have something, again, that the majority of the nitrogen is in the form of ammonium and urea, you know it's acid. If you have something over 20% of ammonium and urea, you know that it's going to be acid. So something like 20-10-20, it's also an acid fertilizer. And then something like 17-5-17, you can see it's only 20% of that nitrogen as ammonium and urea. So anything under 20% will have to tend a neutral or basic reaction. So again, you can also read the label by looking at the fertilizer reaction. It tells you the type of reaction, whether it's acid or basic, but you can also make your estimation based on the total nitrogen and make a conscious decision. So now, putting the previous two concepts together, we want to match the fertilizer to the water quality. And if you have low alkalinity, you want to use something that doesn't have too much ammonium, like I mentioned earlier. If you have a lot of alkalinity, that means that every time you're adding that dissolved limestone to your container, so you want to go into a more acid fertilizer. But if you have a really, really high alkalinity, then you want to make sure that you use acid injections as well. And if anybody's interested and has this problem, we can talk more about it. But the bottom line is that putting everything together, you can go to backbucketgrower.com, and then you can input that information that I just mentioned, the alkalinity, the concentration of fertilizer you're wanting to apply, and it will tell you what's the expected reaction based on standard peat growing media. And now we're going to talk about correcting the problems. We're going to breeze through this. When we think about iron toxicity, again, high iron means low pH. That tends to be the problem. And the causes of low pH can be either from your fertilizer source, like I mentioned, a lot of ammonium and urea, you're injecting acid, or there's insufficient limestone or the wrong type. Maybe it's something that's too slow or there's no residual. So the rules here is If you want to increase your pH to prevent the iron toxicity, you first have to discontinue using whatever's acidifying your growing media and then switch to a basic fertilizer. And that should always be your first tool. You don't want to jump into using limestone as your first tool. You want to see if changing your limestone, if changing your fertilizer helps, especially if the pH, despite being low, it's not extremely low. If the pH is extremely low, and you can see the ranges there, then you can apply flowable limestone, and you can either use limestone F or potassium bicarbonate. They've been tested for a while. They're both very good. Limestone F has the benefit that it has different forms of limestone, so some of them have a little bit more of a longer residual. Potassium bicarbonate is one that works very quickly. It also has the benefit that's really soluble. One of the downsides is that if you have high electrical conductivity, you shouldn't use this one because the potassium is going to raise your electrical conductivity. And then, of course, you have to test for 3 days, after 3 days, and reapply if necessary. If you have iron applications that were over-applied, of course, you want to discontinue the source, and you want to go back again to using the pH of the growing media as your tool. You want to increase your leaching fraction as well. So I just want to put this photo as a word of caution. One is, if you look at this limestone, you can see that it has a lot of iron because it's limestone that was developed to be used in turfgrass, and they want to keep their plants greener. So if you think about, again, how increasing the limestone will help decrease the pH because you don't want as much iron soluble, this is not a good option for you. So the take-home message for this specific product is to use greenhouse products because they're designed with the end product in mind. And it's not because I want to endorse any company or anything, but I really think that they have put a lot of research and development time to make sure that the products will work well for greenhouse crops. And then if you have iron deficiency, again, one of the causes can be high pH. You can use fertilizers that can help you reduce the acid. You can use acid fertilizers to help compensate for that higher alkalinity. You can also inject acids only if the alkalinity is extremely high. If you go online and search for UNH alkalinity calculator, there you will be able to find how much acid you should be injecting if that's the case. But again, fertilizers should always be your first tool, and then injecting acids should be your second option. Now, too much limestone can also be a problem. Again, you can use acid fertilizers. We talked about 2177. 2177, it's extremely acid. It's like injecting acid alone. So you can use it very cautiously. Never use it in the winter or cold months because it has too much ammonium and you're prone to ammonium toxicity. But it's something that you can use to just reduce the pH really quickly. And then for the future, think about combining a fast and slow reacting limestone. And then if you have insufficient iron, if you suspect that you have that problem, the first thing is to send a sample to the analytical lab, because if you are misdiagnosing the problem and you apply iron to compensate for the problem, either as a drench or a foliar spray, you might run into more problems. So the first thing is, before you think about specifically applying or drenching foliar sprays, you want to be able to be sure that that's the problem. You can start working with the pH, and once you get your analysis back, decide whether you should drench or foliar spray. Very quickly here, a big question that I hear is whether you should drench or foliar spray. So the bottom line is you can foliar spray when the deficiency is not severe. It has the benefit that it doesn't interact at all with the complex soil reactions. We're going to talk a little bit about that pH. Root uptake is not required. So in times when it's too cold, when there's root pathogens or other problems, root uptake foliar sprays are an option. It has the benefit that it has low labor costs because it's easier to apply. Multiple complications are needed, which is a downside, but phytotoxicity is also more likely. So as always, we want to test in a smaller group of plants. And no residual iron is left in the growing media for future problems. And then finally, never apply foliar sprays when the flowers are formed. So everything I said about foliar spray, the opposite is true for drenching. Drenching is more effective when you have severe iron deficiency. Therefore, you don't need to apply it as many times. The drench will depend on the form of the pH and also on the form of the iron and the pH of the growing media. You need the plants to be growing. Again, that can be an issue if we're growing things a little bit on the cold side. It's a little bit more labor intensive because you want to go container by container. And then the benefit is single applications are sufficient, but also phytotoxicity is less likely, so that's a big benefit. I'm going to stop here because I think we are right on time. It might be a good stopping time, Jeffrey. Or do you want me to keep going? I have a few more slides talking about iron forms.
I don't see any questions, so maybe you can take 2 or 3 minutes.
Okay.
Before we end.
Okay. So I'm going to talk then about iron sources because that's also a big question. How do you choose your iron sources? So in our industry, one of the things that we use are iron chelates. So the iron chelates differ in how soluble they are. So if you look at the top line here, we have iron EDDHA. It's very soluble. It doesn't matter what pH we have. Iron EDTA, it works better when the pH is under 6.5. As the pH increases, this becomes less available. And then the other form that we use in our industry is iron DTPA, which is, again, more available at lower pH, and the availability decreases as the pH increases. So most of the fertilizers that we buy that have all the elements usually contain iron EDTA because it's a more inexpensive source. And some of them contain iron sulfate, but iron EDTA tends to be more of an available source and more soluble. Iron DTPA and EDDHA, they're a preferred form if you want to correct iron deficiency. So I'm just going to show you some photos here to make some points. The first one is that if you think about petunia here at a pH of 5.1, you can see that because the pH is low, it didn't matter much the concentration or the form of iron that we use, right? So pH plays a big important role in here, right? If the pH is low, it doesn't matter what iron source you're using. If the pH is high, at a pH that the petunia doesn't like, you can see that, first of all, the iron form plays a role. EDDHA is a better form. You can also see that you will need more of that iron to make it work, and that the other forms of iron don't work as well when the pH is high. So the easiest way when we think about iron problems, again, is to manage pH. Here's another example, calibricoas, and you can see that when the pH is too high, you will have, in order to compensate for that iron deficiency, you have to increase your concentrations. Here we see going from no supplemental iron, 0.5, 1, 2, and 4. You can see that the form and the concentration matter when the pH is off. So you could grow calibricoas at high pH, but you would have to invest on putting more iron in the most expensive form to make it work. And then at high pH, increasing the micronutrient level can lead to improved growth, even in impatiens. We talked about how impatiens is on that general group. Still adding some micronutrients will help. So the take-home message here is that when we think about iron management, we always have to think about pH management. When we're thinking about drenching, spraying, that's a corrective approach and we can use it. But our first layer of approach is let's manage the pH. In order to manage the pH, the first thing you want to think about is not injecting acids or injecting limestone. You want to start with your fertilizers. Use those fertilizers high in ammonium to reduce the pH or low in ammonium to increase the pH. And maybe when you're trying to decrease the pH, you might think about injecting some flowable limestone as well. And then I'm going to stop here, but the optimum pH is important for all crops. We show you impatiens being on that general group, but that doesn't mean that impatiens can grow just at any pH. We have that smaller and narrower pH range, which is optimum for most crops. So you don't want to go to either extreme. And I'll stop here then.
Okay, thank you. Thank you, Rosa. I don't see any questions. Sina, do you see any questions?
No.
Okay.
Nope, I don't see any questions. And my only other, but I have a quick question. A lot of growers do use this Kalox for when their pH is too low. They're instead of a flowable lime versus something like Kalox. Can you address that just real quick?
Yeah, so Kalox, the main ingredient is calcium carbonate, and every time when we think about limestone, I don't have direct experience with Kalox, so that's the first thing I'm gonna say. So it's a limestone, it should work, and from what my understanding is, it's very soluble, so you can apply it. What I said is that I have a tendency to prefer the flowable limestone, the limestone F, for example, because it has multiple sources of limestone, and they have been tested a lot in container production, and you can see that the limestone F has a tendency to maintain the pH a little bit more over time because it has those different limestone sources. So I think that's a strength that Kalox doesn't have, but I think Kalox is something that I should try myself personally, but just by looking at the labels, I think that's my preference.